Hello, everyone. Welcome to our presentation. Today, we're diving into a comprehensive guide to linear and polynomial regression. The title says it all. This will be an in-depth look at these important techniques. We'll start with the basics of supervised learning, then move on to more advanced optimization methods, and explore a variety of real-world applications. I'm excited to take you through this journey, so let's get started. Let's dive into the second slide, which provides an overview of linear and polynomial regression. We'll start with an introduction to linear regression itself. This method is fundamental in supervised learning because it helps us model the relationship between our features and a continuous target variable. Next, we'll look at optimization methods. These are essential because they help us find the best parameters for our model. Think of optimizers as the tools that adjust the model to fit the data as closely as possible, minimizing the errors. Speaking of errors, the objective function in linear regression is typically the mean squared error, or MSE. This measures the average of the squared differences between our predicted values and the actual data points. Minimizing MSE ensures our model predictions are as accurate as possible. Now, let's talk about the model family. Linear regression belongs to the family of linear functions, which are characterized by weights. These weights determine the slope and intercept of the line that best fits our data, essentially shaping the model's predictions. The classic algorithm used here is ordinary least squares, or OLS. It works by minimizing the sum of squared errors between the predictions and the actual targets. This process finds the most suitable line that represents the data. Finally, we touch on the basics of supervised learning. In this paradigm, models are trained to predict outputs based on inputs, with the goal of minimizing an objective function like MSE. Linear regression is a key example. It models the relationship between features and a continuous target through a simple, yet powerful linear function. Let's dive into some calculus concepts that are essential for understanding optimization in regression models. First, visualizing derivatives with quadratic functions really helps us grasp how derivatives relate to the slopes of tangent lines. When we look at a quadratic curve, the tangent line's slope at any point tells us how the function is changing at that moment, giving us insight into its behavior and rate of change. Next, let's talk about the gradient. Think of the gradient as a vector that contains all the partial derivatives of a function. It points in the direction where the function increases the most steeply. This is crucial in optimization because following the gradient guides us toward the maximum or minimum of the function. Now, understanding partial derivatives is fundamental. They measure how a function changes as we vary one variable while keeping others fixed. This allows us to analyze the influence of each individual variable on the overall function, which is especially important in multivariate regression. Moving on to the role of derivatives in optimization, they serve as the core tools. The derivative tells us the instantaneous rate of change for a univariate function, helping us determine the direction and magnitude of adjustments needed to improve our model. Finally, in 2 dimensions, the gradient is orthogonal to the level curves, those contours of equal function value. The gradient always points perpendicular to these curves, indicating the direction of greatest increase. Recognizing this relationship is key when navigating the landscape of our functions to find optimal solutions. Let's talk about the initialization of parameters. When we start gradient descent, we need to set initial values for our parameters. Think of these as the starting point for our optimization journey. These initial parameters are crucial because they influence how quickly and effectively we find the best solution. Next, we move to gradient computation. At each step, we calculate the gradient of our objective function with respect to the current parameters. This gradient essentially tells us which direction to move in to reduce our error the fastest. It's like finding the steepest slope downhill. Then, we update our parameters. We do this by taking a step in the opposite direction of the gradient, so downhill. The size of this step is determined by the learning rate, or step size, which controls how big each move is. Choosing the right step size is important to ensure steady progress without overshooting. Finally, we check for convergence. We repeat this process, computing gradients and updating parameters until the changes become very small. At that point, we can be confident that we've reached the minimum of our objective function and our model parameters are optimized. This entire process, initialization, gradient calculation, updating, and checking for convergence, is the core of the gradient descent algorithm. It's a fundamental method that guides us toward the best fit line or curve in regression analysis. Now, let's take a closer look at our application overview. We're focusing on predicting diabetes risk based on body mass index, or BMI, using the UCI diabetes dataset. This dataset primarily centers around BMI as the key feature, along with an intercept term, to help us understand the relationship with diabetes risk. Speaking of the dataset details, it includes various features, but our main interest is in BMI and how it correlates with a diabetes risk score, which can range from 0 to 400. Our goal here is to analyze how BMI influences the likelihood of developing diabetes. When it comes to modeling, we're using a linear approach. The model is expressed as f theta of x equals theta 0 plus theta 1 times x1, and so on, up to theta d times xd, which we can also write as theta transpose times. This formulation allows us to incorporate multiple features, including BMI, to predict the diabetes risk score effectively. Finally, the data visualization provides valuable insights. By plotting the training data, we can see the relationship between BMI and diabetes risk. This visual understanding helps us grasp how BMI impacts the risk score, which is crucial for building accurate predictive models and understanding the underlying patterns. Let's take a closer look at the mean squared error objective, which is central to both linear and polynomial regression. This objective guides us in adjusting our model parameters to make better predictions. When we implement MSE and its gradient, we enable optimization algorithms to work effectively. These algorithms iteratively tweak the parameters to minimize the objective function, leading to improved model performance. Now, thinking about the gradient over the dataset, it's calculated as the average of the individual gradients from each example. The formula is the sum over all data points of the difference between our model's prediction and the actual value, multiplied by the input features. This aggregation helps direct our parameter updates in a way that reduces the overall error. For a single example, the derivative of the cost function with respect to each parameter is the difference between the prediction and the actual target, times the specific feature value. This derivative tells us how to adjust each parameter based on individual data points, which is the foundation for gradient descent. The main purpose of minimizing MSE is to find the optimal parameters that make our model's predictions as close as possible to the true data points. When we achieve this, it ensures our model generalizes well and accurately reflects the underlying data patterns. Finally, the objective function itself is defined as the mean squared error, which sums up the squared differences between predicted and actual values across all data points. Dividing by twice, the number of data points standardizes it, making it easier for optimization algorithms to work with. This function provides a clear target for our minimization efforts, guiding us toward the most accurate model possible. Let's dive into understanding the LMS update rule. When we apply gradient descent to minimize the mean squared error, or MSE, we arrive at what's called the least mean squares, or LMS, update rule. This rule tells us how to adjust our model parameters, theta, at each iteration. Specifically, theta at the current step equals the previous theta minus the learning rate, alpha, times the gradient of our cost function with respect to theta. Now, this step size, alpha, is really important because it controls how big our updates are. Too large, and we might overshoot the minimum. Too small, and the process becomes slow. As we iterate, these updates gradually improve the model's fit to our data, in this case, the diabetes dataset. Over successive iterations, you'll see the mean squared error decrease, indicating that our model is learning and getting better at predicting. To visualize this process, imagine the regression line gradually adjusting itself as the gradient descent proceeds. This graphical view really highlights how the optimization is happening step by step, with the line moving towards the best fit. This entire process exemplifies supervised learning, where our model learns from labeled data, using a gradient-based optimization method. It's a straightforward yet powerful way to see how models improve through iterative updates. Finally, focusing on linear regression, gradient descent provides a clear, iterative method to refine our model parameters until we reach an optimal solution that best fits our data. Let's dive into Slide 8, where we explore the comprehensive guide to linear and polynomial regression, focusing on ordinary least squares and the normal equations. The normal equations are fundamental because they connect our features with the target variables, allowing us to compute the regression parameters precisely. When we apply this approach to the diabetes dataset, we get parameter estimates that help us predict diabetes risk based on the features we have. One of the main advantages of OLS is that it allows for direct calculation of these parameters without needing iterative methods. This makes it quite efficient, especially for small to medium-sized datasets, and since the objective function is convex, it guarantees finding a global minimum. The optimal solution for minimizing the mean squared error, or MSE, can be expressed with this formula. Theta star equals the inverse of x transpose x, multiplied by x transpose y. This formula gives us the best possible parameter estimates for our linear regression model. To recap, OLS provides an analytical, straightforward solution to linear regression problems by solving these normal equations, where x is our design matrix and y is the target vector. Now, let's dive into polynomial regression for nonlinear relationships. Imagine we're looking at how BMI relates to diabetes risk. A simple linear model might not capture the true complexity of this relationship, but by using a degree polynomial regression, we can improve the fit significantly. This shows the practical advantage of polynomial regression in modeling more intricate, nonlinear patterns in data. When we train with polynomial features, what we're doing is transforming our input into a new feature space, essentially creating a vector that includes x, x squared, x cubed, and so on. By fitting a linear model on these transformed features, we're able to fit a polynomial curve to the data. This transformation is key because it allows us to leverage the simplicity of linear models to capture complex nonlinear relationships. The polynomial features turn our input into a form that makes fitting a curve easier and more flexible. Now, extending linear models with polynomial features means we're not just limited to straight lines. Instead, we can model curves of any degree. The general form of such a polynomial is f of x equals times x to the p, plus ap1 times x to the p minus 1, and so on, down to the constant term. In summary, by transforming our features into polynomial terms, linear models can effectively capture a wide range of nonlinear patterns, making them a powerful tool in our modeling toolkit. Now, let's look at multivariate polynomial regression and nonlinear least squares. These methods are powerful because they allow us to model complex relationships between multiple variables. One key advantage is that the normal equations provide an efficient way to estimate the parameters, theta. This makes solving even for complicated models computationally feasible. Moving on to nonlinear least squares, this technique generalizes polynomial regression by using arbitrary nonlinear feature maps, which we denote as phi of x. What's interesting here is that even though the feature map can be quite complex, the model remains linear in the parameters. Expressed as f theta of x equals theta transpose times phi of x. This linearity in parameters is what keeps the estimation process manageable. Now, in polynomial regression specifically, we use a feature map that includes all polynomial terms up to a certain degree p. This transformation allows us to capture nonlinear relationships using linear models, which is pretty neat because it simplifies the process while still modeling complexity. When we extend polynomial regression to multiple variables, it becomes multivariate polynomial regression. For example, with two variables x1 and x2, our model sums over all combinations of powers up to degree p, like a sum over I and j where I plus j is less than or equal to p. Of the coefficient a ij times x1 raised to I times x2 raised to j this way, we can model interactions between variables quite flexibly. Finally, let's consider some applications and advantages. For instance, we can model periodic functions using sums of sines and cosines, which is very useful in many real-world scenarios. This approach allows us to capture complex, nonlinear relationships while still leveraging the simplicity and efficiency of linear optimization techniques. Overall, these methods expand our toolkit for tackling a wide range of modeling challenges.